Hi everyone. This video is on a decision curve analysis and how to run it in a Shiny app using the Model Builder tab. A decision curve analysis is something that we can use to help us once we've created a prediction model. We can then find the best threshold to determine when we will act or not act based on that prediction. So we often make that decision based off of using that mean or median prediction because for the most part our regression models are going to help us to predict that average value such as the mean. We can get a prediction that would give us our best results for that data based off of that mean or median prediction. But the best way to do to determine a threshold is to get information from our stakeholders or our clinical experts. They would most likely see things differently than just using that mean or median value. They would, especially if our outcome has a high degree of risk associated with it. So they might act differently than what mathematically works out as the best option. So we want to use our decision curve analysis to help identify a good threshold. And we're going to do that in the Shiny app. So I'm going to go ahead and launch the Shiny app. I'm clicking on the Run App button in the server.r file. And this is from my Shiny app, which in the description you can find the GitHub location that has my server and UI files for my Shiny app. Okay, so we're going to go to the Model Builder tab, and I'm going to use two different data sets. One will be for a logistic regression and a Cox Proportional hazards model with censoring, and the second file will be for an ordinary least squares or linear model. And I'm citing the study by Vickers, and I'm going to scroll down so you can see where that's at. Right now we're in the Model Builder tab. I have how to run a model at the very top. Then our model results would be directly below that. But further down is where we have information about the decision curve analysis. And here's that Vickers citation that I just highlighted. And right above that, we actually have information on selecting a cutoff level that would give us our classification results, such as sensitivity, specificity, our false positive rate, and our false negative rate. But once you do that, the next step that you can do is for the actual decision curve analysis. And what I'm highlighting in blue right now would give us some more information about some more notes on a decision curve analysis. And below that we have different ways to modify that decision curve. So let's go back up to the top. We're going to begin with the logistic regression model. In the Vickers article, they used just a logistic regression model. I've tried to make some modifications so I can run it for different models, such as a Cox Proportional hazards model, as well as a linear regression or an ordinary least squares regression. There is some more work that I need to do, but I thought I would put this video on right now just for those who may already be considering that logistic regression, or maybe even if this can be helpful for people using other regression models. I'm going to put the video up now, and once I improved the functionality of what I'm using in this Shiny app. I'll update that video and I'll provide better examples. I'm going to use the retinopathy data set from Terry Thurneau's survival package. He did a survival analysis, which is the best way. His approach is the best way to analyze this data. But I needed to find something. I needed to find a data set that's easily available, so that it can be found on the in the Shiny app, and he has his data available through his survival package, which is used in this Shiny app. So the data is already there, and I also needed a data set that has some sort of risk score. So this retinopathy data set does have a risk variable in there, and so if you do have a data set that where you're only getting a prediction, maybe it's hand scored, or maybe you're getting this from some other source where that prediction's already calculated for you in a data set, then you can see, or maybe that goes from a value of 1 to 10. You can use the decision curve analysis to help you figure out a good threshold, and it will provide that information for you. So whether you're building a model and you're running it yourself, or you've already gotten the prediction from a different source, this should help in both of those circumstances. So let's begin. We're going to go to step 1, and we're going to type in the data set name, retinopathy. And in Terry Thurneau's data set, this is diabetic retinopathy, and the outcome is loss of vision or blindness. A special consideration with this data is that for each patient they have 2 observations. So really this isn't the best way to analyze this data. I would take a look at Terry Thurneau's work to see how he analyzed this data. We do have an issue with independence because each observation belongs to 2 observations belong to each patient, so there is an issue of clustering in this data. So this isn't the best way to do it, but it's still a good example of how to use a decision curve analysis, the mechanics behind doing it in the Shiny app. So at step 1 we have our data set, retinopathy, which is spelled RETINOPATHY. And so we're going to go down to step 3. We're going to put in our outcome, which is status. 1 if there's blindness, 0 if there's not. And we're going to add in our predictors. They are laser, eye, age, TRT, which I believe is treatment, and then finally risk. And we're going to, at step 5, we're going to select a logistic regression. Click yes. We have our model results below. We see on the top right that our C statistic, or our area under the curve, is 0.672, which has a fair predictive ability. So let's take a look at the model results. And we're going to go to our different tabs now. We're going to go to the summary tab to give us an idea what the results look like, and we see that age tends to be associated with a higher risk for our TRT variable in the second row. It appears that for those who I'm guessing had some sort of treatment, their risk has decreased. This dashed vertical line is for an odds ratio of 1, so everything above indicates greater risk, everything below a lower risk, such as the treatment variable. And then when we look at that risk variable, we see that those with higher risk scores appear to have a significantly higher risk. For laser, it's doesn't seem to be a significant difference there. For the eye, it actually does appear to see that we have a significant difference between our right and left eye. We'll look at the variable importance in this next tab, in the importance tab, and we see at the very bottom TRT does have, it is the most important predictor, meaning that the biggest difference is what we see between those with a treatment value of 1 versus with those with the treatment value 0. So the variable that has that may be the best at predicting our outcome would be TRT, which is treatment. Risk also is a stronger predictor as well. An eye is significant at the 0.05 level, but just barely. So now we can go to the partial predictions tab, and we can see the direction of our associations in the data between our outcome and our predictors. And we see that on the top left, as a risk score increases, so does the risk of vision loss or blindness. And we see next to it is treatment, and we see there's quite a big difference where those that do have a treatment value of 1, which I believe is that this is a treatment group, their risk is a lot lower, significantly. And so let's go back to the Model Builder tab. We've, at the very top, we entered our model, we ran the model. We see our results. We do have some predictive ability that that we may want to now set a threshold to. So we're going to scroll down. We're going to go to the section where it reads as describe the predicted values. As I mentioned earlier, that one way that people may set thresholds is to use the mean or the median of our predicted values. That would probably give us the best area under the curve, because our model is predicting towards the mean. So if you can just go ahead and use that, it would give you the best area under the curve, but it probably wouldn't be the most helpful information, at least not to our clinical experts working with this data. They may, if the outcome is very serious, they may want to actually set a threshold much lower than the mean or the median, or maybe even if it's if the effort to act on that prediction's really not very high. So if there's low cost in our intervention, that may determine where we want to see our risk score. Or maybe if the cost of the intervention is risky itself, then we may want to modify that threshold. So sometimes we may want to have a very low threshold, but other times we may want to have a very high threshold value. And in Vickers, he has a really good discussion about that. Their prostate cancer it's an invasive test, so there's high risk in the test itself. So they go through a very good description of how clinicians may want to base that decision of what their threshold is based on the risk to the patients themselves. So let's just copy that value for the at the 50th percentile of our predicted score, and we're just going to give it that. we're going to use that as a place to start. So we'll scroll down and we're going to go to the section that reads as examine sensitivity and specificity values from a threshold on predicted values. So that value that we just copied, the mean predicted value, or the median predicted value, we're going to enter that here. That's step 1. Step 2 is for a survival model, which we'll cover later. Step 3 and 4 are if we have loaded an existing model or a prior model. So maybe we had to come back to this at a later point and we just wanted to load our model, and we can do that in that data tab where if we've saved our model as our data, we can load it, enter the name here. Maybe I called it model 1, and then I'd click yes on step 4, and then we would in doing so we're going to give us the ability to do the decision curve based on that existing or prior model. But we just built a model, so we're just going to go ahead and use it as is. So we're going to skip 3 and 4. I can highlight the bar colors. So at step 5 I have green selected, and this is the default setting, and so is red for step 6. And what that would do is show that for our sensitivity and specificity, or our true positives and our true negatives, those bars are going to get highlighted green so we can see how our true predictions differ from our false predictions based on our threshold. And those, when we're wrong, or our false negatives and false positives, those bars will be highlighted in red. And we have a threshold line color, and then we can see where that threshold is at and how it helps differentiate between our true and negative predictions. We do that with that blue vertical line, and we can increase the line width to help us see that blue line better. It's step 8. And for step 9, we can increase the number of histogram bars. If we have very wide histogram bars, we might not get enough detail to see what those predictions look like, or that threshold looks like. And if we have a lot of data with a lot of different prediction values, then we'd probably benefit by increasing that from that standard default setting of 15. And then also at step 10, we can answer yes or no. If we leave it as no, then both of our the two graphs that we're going to look at below will fill up the screen, I guess. And if we click yes, then the graph with the highest frequency will determine the graph with the biggest or the highest bars, and then for that smaller frequency, then we'd see smaller bars for it. So it'd put it in perspective of which group has the highest frequency. And so we're at step 11, and so let's just click yes, and that gives us our graphs. On the upper half, those are graphs. That histogram is for those where our outcome is, in our case, a status value of 1, and on the bottom, that represents a status value of 0. So on the top half, those are the patients who actually were that did have a positive an outcome of yes or an outcome of 1. And so and then below that, those are who had their outcome of 0 or no. So on the top, we can see that in green we would have what we call our true positives, and we refer to that as sensitivity. And these that blue vertical line, I can barely see, so I'm going to go up to step 8, increase that value to 8 so that I can see where the threshold is at. And on the top section in green we have our sensitivity, and to the left we have our false negatives. And in this lower half we have, in red to the right of the bar, we have our false positives. So if we used that threshold of that we at the median, then it would, in this bottom half, we would see that about 41% of our predictions for those who actually did not have blindness or vision loss, 41% would be incorrectly predicted as those who could have blindness. So we see what the our mistake and our false positive is. But to the left we actually see what our true negative or our specificity is. And above we can see that if we, using our current threshold, we got about 64% of those who actually did have blindness that we were able to predict. And on the top right we can see that of the title, we can see that our area under the curve is 0.614. So it's not bad for a threshold. We can modify this threshold. We can move it to the right or left, and we would see that by doing so it'll change the number of true and negative predictions that we have, and also would change the area under the curve. And so this would be a good time to include your stakeholders or your clinical experts. They might find that depending on what the risk or the benefit of the intervention is, they might want to move this threshold. But we're going to, we'll continue with this threshold, so we can take a look at our results. And the results that we see below the graph are for our classification results, such as sensitivity, specificity, false positives, false negatives. We can get an accuracy rate as well as an error rate. And then the section below that we get information on our predictive values. For example, we find out about our positive predictive value as well as our negative predictive value. And the section below that would be our frequencies, and it would be the frequencies for sensitivity, specificity, false positives, and false negatives. And then the section below that would actually be for our decision curve analysis. And for the decision curve analysis, there's a net benefit. That would be the benefit in terms of true positives. So if we have a larger true net benefit, then that would mean that this green section above on the top half, which is our sensitivity, we would see the difference between our true positives and our false positives increase. So we would have more and more true positives than false positives if we have a bigger net benefit. And the complement of that would be the interventions avoided. And that would be what's to the left of that blue vertical bar. So if we have more and more, with a more accurate model, and if we're using that model, we may find that it's actually more helpful to avoid interventions. If we have a very costly intervention and maybe we consider the outcome not all that important, maybe this could be missed appointments or missed or miss check-in information at the very end of a study. Maybe the effort to get certain information may may cost more than the benefit of getting it. So there are probably some really low risk outcomes where the information may not be as vital at that point. So if there's a benefit to avoiding an intervention, this is when that intervention avoided information may help. We may find that because a very predictive model is good at identifying those with the outcome as well as those without the outcome, we may find benefit to knowing the interventions avoided. So again, if that number increases, then we would say that there's a bigger difference in saying that more and more patients are less likely to have that outcome. So I have some more information about the decision curve analysis, about net benefit and interventions avoided. Another strategy that Vickers mentions is that we treat all. If it's a very serious intervention, it's a very reasonable strategy for, say, clinical staff to treat everybody, to intervene for all cases if the outcome is very risky. But we can compare how our model performs between our net benefit and the all-treated approach. Okay, so now that we have set a threshold for our model that we ran, now we can take a look at our net benefit. And so if we come down to this section below it, which reads as decision curve analysis, we can go to step 1. Right now the default setting is for the net benefit. We can select the legend location in 2, select our line colors. We have the our line for our net benefit, the all-treated approach, and none-treated approach, which would just be we don't act on it. Maybe this is an outcome that we're not especially worried about, so we may not act on it at all. And so we can also select our line width. We can modify our X and Y axes. And so we're just going to go ahead at step 9 and click yes to run our graph. And so what this graph can do, which is discussed in the Vickers paper, is give us a visual representation of when the model gives us the most benefit, or in terms of our net difference between true and false positives, or what our interventions avoided can look like based on the same model. So we can see that with the lower threshold we get a bigger net benefit. So that'll be the case every time where we would catch more potential outcomes by setting a lower threshold. That's just kind of how it would work out with any model, that if we set a lower and lower threshold, then we theoretically would always get more and more potential outcomes, potential negative outcomes such as vision loss or blindness. Let's go ahead and modify this. We only on the y-axis we really only need to go up to about 0.3, and on the x-axis it looks like most predictions fall between about 0.2 and 0.6. I'm just going to reset our maximum or our upper x and y limits. So for the x, I'm going to set it to about 0.6. And for our y-axis, I'm going to set the upper limit to about 0.3. Okay, so that gives us a better look at our model. I'm going to actually increase the line width. Okay, so that gives us a better view. Notice at the very bottom, that gray line represents the none-treated approach. It's the opposite of the all-treated approach. And so what we can see with this graph is that what's the benefit, the net benefit for our model, which is in green. And we see that across our predicted values, and I think our range in predictions, when you convert it over to probability, goes from about 0.2 to about a little over 0.6. So that range doesn't go all the way from 0 to 1, but it goes from about 0.2 to 0.6, which is not uncommon for the model with our current C statistic or the area under the curve. But what we can see is that with a lower threshold, we get a bigger net benefit. And generally that using a model, we can see because the green line is above that black dashed line of the all-treated approach, we see that across our predictions, the model's a better way to go. And we see that if we increase our threshold, we get a lower net benefit. And the net benefit is on our y-axis, and our threshold level is on the x-axis. So we can see that as we move our threshold up, our net benefit actually goes down. So it's if we did a cost benefit analysis, and we would see no real point in setting too high of a threshold, especially if it's a very risky procedure. We would see that we do get a benefit from this model. But suppose we actually just want to avoid interventions. What we can do then is change that net benefit to, at step 1, and select interventions avoided. And we see that it kind of goes, I need to reset my upper y-axis limit at step 8. Okay. And I probably also need to do the same for my x-axis. Okay, so I'm going to set that to 0.8, and I actually might move it on the lower limit. I might change that to 0.1. Okay, so this also gives us an idea that kind of the opposite idea, that if we have too low of a threshold, then we're not going to really avoid too many interventions. But if we do increase our threshold, then what we can do is avoid unnecessary interventions or expensive interventions that may have expensive in the sense of not only cost, but the impact on the patient, as well as it may interfere with time that they have. So we may see a benefit from this graph on interventions avoided. We may find a benefit of where we might want to set our threshold. In this case, a higher threshold equals more benefit. And this is in terms of interventions avoided. And we see that on the y-axis. Okay, so that's how we would set our interventions, or our threshold. And below that we have our decision curve analysis. These are our results. We have different threshold levels, and these threshold levels are converted from our logits into probabilities. And we have, this just gives us an idea what these levels are. and these levels are set for 7 predicted values of quantiles, and those are at the 5th percentile, the 10th percentile, the 25th percentile, the 50th percentile, 75th, 90th, and 95th. When there are less than 20 unique values, what the Shiny app will do, it'll just give you values for each individual score. So maybe if this is the case where we get predicted values, maybe there's a hand-scored risk assessment, maybe it goes from 1 to 5 points or 1 to 10 points, we can see what those predictions are for each of those different scores that are assessed by hand or from a different source other than our model. So we may have a model that already exists, and it may get implemented at the bedside, or as a paper copy, or as notes produced electronically for each patient. So we'll go ahead and do that next. But I just wanted to mention that in this output below, we get information on the threshold level, the net benefit, the rate for each, for treating all, and the interventions avoided. And we have 7 different values, and those represent the cutoffs. This is kind of a general graph that gives us an overall idea about the range of predictions, but if you wanted to find one for a specific value, you would enter a cutoff at step 1, and if I modify this cutoff, the values will change below for our decision curve analysis. For example, at this current cutoff, the net benefit is 0.0925. I'm going to increase it slightly to 0.4, and we see that it's slightly changed. If I keep doing that, it'll just keep changing. Yeah, so the net benefit keeps going down as I move my threshold up, which isn't surprising. But let's go back to the top, and what we're going to do is we're only going to use one predictor at step 4, and that's that risk score that I believe is it comes from a hand-scored clinical rating. Okay, so we're just going to use one predictor, and maybe this is you're only getting one prediction score, or maybe you've already developed a model and now it calculates a predicted score for you, and so you're not doing a model from scratch, you're using predictions of a model that's already been in place for a few months. But you can also do decision curve analysis based off of maybe new data from an existing model. So let's go ahead and use just that risk score, which we're going to hypothetically consider that as a bedside assessment, or a predicted value from an existing model. So we see that the C statistic, or area under the curve, has decreased because we don't have as well of a predicted model as we did in our last example. Okay, so for this, that risk has six different values. So we don't really, so we're not going to see as many histograms or as many bars as we did earlier. But that's okay. Maybe all of our it wouldn't be uncommon to see a 5-level bedside prediction on risk. But we still get we get the same information. We get net benefit, all treated, interventions avoided. Let's modify this just a little bit. Okay, I think this is probably closer to our last model. It's important to note that part of that formula is where we set our cutoff level at. So we can set it to 0.45. It'll move over a little bit, but by doing so, that threshold level also determines part of that formula. It would be the numerator, I'm sorry, the part of the denominator for the model, and actually part of the numerator as well. I'm sorry, it would be a weight, and it would be that PT value. That's the probability that it's true or a specific threshold. So in that formula for net benefit as well as interventions avoided, that threshold, which in this formula is represented by PT, gets modified. So even though there's really no values between negative 0.04 and negative 0.05, having negative 0.05 gives you a different value than negative 0.4. So it's just one thing to be careful about, is that where you set that threshold at, even though it may not represent any patients at all, it could give you a different net benefit result. I'm going to stick with negative 0.45 just because that's close to what we originally began with. Okay. So let's go down to the decision curve analysis part. Because we don't have a lot of data and we only have a few levels, and mainly because we only have a few levels in our risk score, we can kind of see something odd happen with our the model results. That green line increases or decreases in this example, kind of an odd way, where these 2 points, where that higher threshold actually shows a slightly higher net benefit. It's probably easier to look at if I can increase or if I can modify the X and Y limits. I'm going to do that. Go back to the original values or the values I had earlier, and you can see that in that green line it increases a little bit between 0.35 and 0.45. I would consider that as just part of the issue of having a predicted score that has a low range, I think 5 or 6 values. So how I'd interpret that is really this is probably just an erroneous issue because of how we calculated it. Where we have our threshold is at, and I'm using these 7 quantiles, and because I have less than 20, it's picking each predicted value and basing it off of the threshold value associated with it. So I would consider this as a downward trend, and I think I would ignore this kind of how this net benefit increased slightly for this higher threshold value. But overall, it shows that you probably do benefit from the model, that the C statistic, or the area under the curve, was below 0.6, so it's not as predictive as the model that we were just looking at. But overall, I would say that there is a benefit to the model, and the net benefit probably would be lower at this point, but that would be an issue with just how it's calculated, and it uses that threshold level in the formula. Okay, so now let's look at interventions avoided. and we're kind of seeing a similar trend where it's higher on a spot that we'd expect it to be lower, or in this case it's lower than for interventions avoided, it's lower in the spot than it should be. But again, it shows some benefit in terms of net benefit and interventions avoided. And we get more information here. Okay, so I'm going to go back to the very top, and I'm going to show you something that I have built in. It's a function that's in the code, but it's not shown anywhere except for the direct function call. So let me add in these different predictors: laser, eye, age, TRT for treatment. Okay, and actually I think it would be easier if I go back to that model that we're just looking at with just the risk score. So I'm going to scroll down to the decision curve analysis section, and okay, it's actually, I'm sorry, it's above the decision curve analysis section. It's in the examine sensitivity and specificity values from a threshold on predicted values. It's below that heading. If you come down to the second to last line of this section, and you highlight this function, FNCAUCDCA class, if you highlight that, copy it, go up to the Describe tab, enter it in step 1, go to step 2 and select results. What it's going to do is give you all of the different classification results, such as sensitivity, specificity, false positives, and false negatives. It's going to show you the values associated with each of those different predicted values. So for this risk score, it has 6 levels. It actually starts, and I have it described in the in that last section. And in the Describe tab, I start at the second level, or the second predicted value, because you can't really have a threshold for that first level. If you use that first level, then that would mean that if that predicted value had 5 levels, then it's the equivalent of all treated. If you use that first level as your cutoff, then everything that gets a value of 1, 2, 3, 4, and 5 would be considered would fall under that threshold. So there's really no benefit of selecting all levels for your threshold. So I go on the second level, starting at the second level, and that's where that threshold would be. So starting with that second predicted value, it gives the threshold for that value. We change that into a probability or a proportion, and then we get the area under the curve, and then you can see that around the 4th level, for that 4th value, we have our highest area under the curve. And you can see that the sensitivity and specificity, the false positives and false negatives for that rate. So what it's going to do is compare every one of your predicted values and identify what gives you the best area under the curve, sensitivity, specificities, false positives, false negatives, the accuracy rate, error rate, positive predicted value, negative predicted value, gives you the N for your sensitivity, specificity, false positives, false negatives, the predicted positive, predicted negative, our net benefit, and our interventions avoided. So if you wanted to rank, if you wanted to select a threshold based off of the prediction performance, it'll give you it all for all your different predicted values, and then also gives you the ranks below. So if you wanted to know what threshold gives you the best net benefit, you can figure it out here, the best area under the curve, or the best result in terms of interventions avoided. So if you copy this function, and actually that line that I have selected that begins with the function name and ends in the parentheses closure, then that'll produce this information for you. So that's one way you can use this to help find you the best threshold. Again, the best way is to get your clinical feedback, or to get to get a level from your stakeholders, but this may be good information to review with them. Okay, so I can also do this for a survival model. I'm going to use the same data set. I'm going to click No at step 2 so I can start the model fresh, changing that outcome to the follow-up time, FUTIME, and we'll use the same predictors that we just ran: laser, eye, age, treatments, and risk. Our censoring variable is status. We'll type that in there. We're going to change this to a Cox Proportional hazard with censoring model. We're going to run the model. R squares, it's okay, it's 0.082. So we're going to look at our next step is to go down to their predicted values. They give us a spot to start. We're going to use let's see. Let me check this model real quick. Okay. Okay, I'm going to use I'm going to use the 50th percentile, 0.02902. I'm going to go down to this section where we can select a cutoff level. I'm going to change, this is because we're doing a survival model, I can change it to a specific model time. Right now it's at a survival model time of 1, but I want to change that to 40. So it gives us different results, and it's important to note that survival in terms of 6 months is a different story than, say, survival at 5 years. So what is difficult about doing a decision curve analysis for any survival model is that we would want to consider survival based on a survival time that we're primarily interested in. So again, 6 months could be a different story than 5 years, and because of that, you really would need some sort of way to distinguish between all the different survival times that you do have. So in other words, you could do a decision curve analysis for each survival time. That's not the best way to do it. Frank Harrell, if you search for his work on decision analyses, he discusses that in a lot more detail. And actually, this approach that I'm going to use is not the best approach to use. And he describes issues with it, and I think those would be good to review on your own, because this approach that I'm covering right now is not recommended by him, and he has a lot of good suggestions and better or more optimal types of studies for that. But for one that we can do with this, for these functions that sometimes are used and have been used in previous work, this is how we would do it. So we'll just leave our cutoff level here that we had previously selected, negative 0.45. And we can see how we split our true and negative predictions based off of whether the patient had the outcome of blindness on the top half or no blindness on the bottom half. Our area under the curve is 0.603 based off of using this cutoff. And we have our information below, our same information. Interventions avoided. I'm actually going to modify these. Right now it's on interventions avoided. I'm changing it to net benefit, and I'm going to modify the X and Y axis limits. Okay, so again, it shows us the same thing, that if we have the model it's better to use the model than not to use a model, especially if we're thinking about the all-treated approach versus treating those with the higher risk. So there is a benefit to the model. If I switch it over to interventions avoided, we'll see that as well. But we can avoid more interventions with the higher threshold, but for net benefit, a lower threshold does give us more of a benefit to from using the model. We do get that information below for these from the percentiles from the 5th to the 95th percentile. If I want specific information on my exact cutoff, then I can get that through step 1 that I have highlighted here under examine sensitivity and specificity values. And we can again see the information here. Because we have survival at each time, I don't have that function built into that command that I use that I can paste in the describe tab. I'm going to get an error from that. So as of right now, we don't have that in this function. At some point I probably will add it, but right now that will not give you information that would compare each of these different prediction or predicted values. Okay, so that's how we do a Cox model. But if we wanted to do an ordinary least squares model, I'll show you that. Okay, so for that we're going to look at chick weights, and it's spelled capital C, H-I-C-K, capital W-E-I-G-H-T-S. And this is I think it's without the S. So I'm sorry, it's spelled capital C, H-I-C-K, capital W-E-I-G-H-T, chick weight. This is a base data set from R. And so I'm going to look at weight. I'm going to use the two predictors of time and diet. I'm going to change that to the linear model at step 5. I'm going to go ahead and run the model. It has a pretty good R-square of 0.75. I'm going to grab the mean value, which is 121.8. And actually, let's see what that should be the same for the predicted values, 121.8. Yes. And so now we're going to scroll down to this section that reads as examine sensitivity and specificity values. For our cutoff, I'm going to paste in that cutoff. I think it was 121.8. And now we can see how it differentiates between our true and negative predictions for those that did have a value at or above 121.8, and those that had a value below that, below 121, are seen in the bottom graph. So we can see it splits between the two fairly well. Our area under the curve is about 0.898. We can see that those that are above the cutoff are about 94% in our top half, and so that would indicate a fairly high level of sensitivity and specificity on the bottom as well. Again, this is using our own data set, so we may not expect, we'd be surprised, I think, if it maintained that level of discrimination in future data. But below here we get our classification results, our predictive values, frequencies, and our decision curve analysis. The benefit is about 0.32. It's important to note that this is not coming from Vickers' work. I used a similar formula, say for example for the net benefit. I had true positives minus the false positives over n times the part that did differ is in this weight, pt divided by 1 minus pt. I used my quantiles, so I think there's a better way to weight that I'm still working on, but the idea is that if I used a threshold that's at the 50th percentile, then that would be entered as the 50th percentile in this weight. So it's not. It gives us a different weight, and there's, I'm sure, a better way to calculate this weight. But this is not how Vickers did it. Vickers only reported a logistic regression. So for this for an ordinary least squared regression, I'm still working on this. So I would only use this in the directional sense of where you begin to start to see your high predictions, and is it a steep decrease or is it a level decrease? Because we will get results that make no sense, such as negative net benefit, which you can actually get that in a logistic model, which I believe Vickers mentions, that based off of maybe rounding error, you might expect to see a negative value, but not to the extent that we're seeing it, that we would see it in our ordinary least squares model. So let me, before we go any further, I'm going to change threshold. Yeah, that's, let me change that to 0. Okay, so in the overall sense, we can see that there is a benefit to the model. Maybe not so much as in the all-treated approach, and that's probably because we don't have a lot on the low end. Yeah, so for those who had the outcome, you start to see their weights show up around 100. So we just don't have a lot on the low end. If we're looking at when to use a threshold, the model really doesn't kick in until you get to around maybe 75 or 100. Just because we would see that these chick weights are different for those that were on the higher side and those on the lower side. So there's not a lot of benefit to the model just because we don't see a lot of, when you split it this way using the mean, then we don't see a lot of benefit. But when we do have weights that are on the higher side, we do see that the model performs better. And we do see a steep decrease, so maybe the benefit is between that 20th and 40th percentile. And what you're going to notice is that in the net benefit we get really low values. So I would really just use this for an ordinary least squares regression. I would only really use it just to give me the idea that there is net benefit, but more towards the middle values. And anything below 0, I would just consider it as there probably is a benefit to the model, but with these low negative values, and that indicates to me that I need to keep working on how to produce a decision curve analysis on continuous outcomes. But overall, we do see the model performs well, and that we would assume there to be some sort of net benefit, and even interventions avoided would be helpful information for us. So I think in this sense, the decision curve analysis could identify that there is benefit to the model, but you're probably going to go beyond that, and at least maybe not for this data set. Okay, so that's it. That's the decision curve analysis. In summary, you begin by creating your model, and if you have already created a model, you can just skip to the steps further down. But after you build the model, you may want a beginning spot on where to begin with your predictions. You can go to the section where you describe the predicted values, look at the mean or the median, just to give you an idea of where to begin with. Then with your stakeholders, you can begin to you can go down to the examine sensitivity and specificity values from a threshold on predicted values. Begin to enter the information. Go to steps 3 and 4 if you already have a model, once you've entered a cutoff level. And then you can go down to, you can make changes to your graph after you've pressed 11, yes for 11, or before you press yes for 11. After you click yes at step 11, you can get information to show how well your model performs and where that threshold fits in. You can then get information about how the model performs, as well as decision curve analysis information in terms of net benefit, which is your difference between your true positives and your false positives. And you can also look at your interventions avoided, and that would be the difference between your specificity and your false negatives. And here's your decision curve analysis citation that I think is a great read. This is a very helpful process, and it really explains the benefit of doing a decision curve analysis. And if you want information to show you how each of your different predictions performs in terms of net benefit and interventions avoided, as well as sensitivity, specificity, and all of your other classification results, you can copy this part I just highlighted for this command, this built-in command, and then go to the describe section, and then it'll provide that information for you. So that's it. Thank you.